Welcome BC students. We're going to talk about separable differential equations today. This is a topic that you did see in AB, just at a slightly easier level. We're going to be looking at how to solve a separable differential equation. We've got y and x. The first thing that I have to do is get all the variables on different sides. I want all the y's on one side, all the x's on the other side, so that I can integrate with a single variable. So what's happening here? Okay, so with this dx on bottom, I'm going to need to multiply both sides by dx. I've got x squared plus 4, we have a dy. If I multiply both sides by dx, then I have x times y times dx. The dy and the dx, those have to be in the numerator, so we've got our proper form for integration. Now I need to divide by y and divide by the x squared plus 4. I need the x's over here, the y's over there. That's what I'm going to do. Okay, let's divide both sides by y, divide by y, and also divide both sides by the x squared plus 4. I'm just separating variables right now, hence the name separable differential equations. Divided by x squared plus 4. Delightful things will happen here, these y's. Y divided by y is 1. X squared plus 4 divided by x squared plus 4 is 1. I'm going to scroll up for more space. So here on the left, I have 1 over y times dy. On the right, I have x over x squared plus 4 times dx. And once you have the variables completely separated, you can integrate both sides. So that's what I'm going to do. Integrate both sides. On the left, the integral of 1 over y is the natural log of absolute y. On the right, I'm going to use substitution to solve that integral. So let's scroll up for a little bit more space. Let's see. If I'm using substitution here, when I'm looking for substitution, a denominator is a great place to look. I noticed the x squared plus 4. That's probably what I'll use for you, because the derivative of x squared plus 4 is 2x. And look up there. That also has the same variable part, the same x. A difference of a constant is totally fine. So I'm going to let u be x squared plus 4, so that the derivative of u with respect to x is 2x. And then I will divide by 2x, multiply by dx, try to get dx alone. We've got du divided by 2x is dx. So now I can substitute in. We are integrating, I've got x over, and instead of x squared plus 4, I've got u. And then instead of dx, I have du over 2x. X divided by x is 1. That 1/2, the 2 on the bottom, that's like we have a 1 on the top, a 2 on the bottom. The 1/2 is going to factor out. So I have the natural log of absolute y. We've got a 1/2. The integral of, let's see, 1 over u du. Let's integrate that. I've got a 1/2. The integral of 1 over u is the natural log of absolute u. And here I'm going to add a constant. When you're doing these separable differential equations, you only need to add a constant on one side. I could add constants to both sides, but then I could just subtract the constant from the other side and combine them all into one constant. Let's see, we've got the ln absolute y over there. I'm going to put the x back in. So the natural log of absolute y is 1/2. The natural log of absolute, okay, u is equal to x squared plus 4. Let's put the x squared plus 4 there, and then plus a constant. I'm going to scroll up for a bit more space. Okay, I'm going to want to exponentiate both sides to get rid of the ln and solve for y. But before I do that, I'm going to use a log rule. I'm going to take this 1/2 multiplied outside the log and make it an exponent on everything inside the log. Okay. We've got the natural log of absolute y is the natural log of the square root. A 1/2 exponent is a square root. Roots are on the bottom of the tree, square root of this to the 1. And we've got the, do I need absolute values on x squared plus 4? No, you're right, we don't. Because x squared is always positive, add 4, still always positive. We've got x squared plus 4 here. It's beautiful. And that constant is separate from the natural log there. Okay. Whew. Well, let's use our lovely number e as the base of our exponentials there, doing it to both sides to keep things equal. Notice all of this is in that exponent. And so we can do this lovely special thing that we did back in AB as well, where we can make a equal to e to the c. Because if you're adding in an exponent, that's like multiplying two separate powers. Multiply with powers, you add the exponents. And so I can write this. Ooh, wait a minute. Woo, delightful. Okay, y is, we've got an a, and then that's our e to the c, that part. I'm just putting it out front. And then we have this e to the ln root x squared plus 4. We've got that. Now, e to the ln, those undo each other as well. So remember, when those undo, this is down on the ground. When those undo each other, that inverse operation happening. So we've got y is a times root x squared plus 4. Okay. Well, I'd like to know what a is. And we have a point. Up at the top, we're given, ooh, was it 2, 0 or 0, 2? Let's check. Zero, 2. Glad I checked. Okay, the point 0, 2, and I'm going to plug that in. So 2 is equal to a root 0 squared plus 4. Okay, so 2 is equal to a times root 4. That's 2. Yeah, so a is 1. And now I've got my formula. Let's put it in purple because that brings me joy. We've got y is a, which is 1, times the root of x squared plus 4. And I don't really need the 1 there. It doesn't change anything. So I'm just going to write y is the root of x squared plus 4. This is the particular solution to the differential equation. It's called a particular solution because we used a point to figure out the constant. If we weren't given a point and we were unable to figure out the constant, it would be called the general solution to the differential equation. So before I found the constant, it was the general solution. By plugging in a point, an initial value, it's an initial value problem, and we found the particular solution. Have a lovely day.